Hello, my name is Justin Berggren. I am talking today about the Crj200 and specifically the Environmental Control System, the ECS, for Avia435. And the Environmental Control System, again ECS, is in charge of the air conditioning and the pressurization system for the aircraft. It provides temperature and pressure regulated air, and this is used for ventilating and pressurizing the cockpit as well as the passenger cabin and as well as the cargo compartments. It provides cooling air for avionics and the equipment racks, so that'll keep all of the aircraft's systems all cool so they don't overheat, so everything's working well. And then the exhaust air from the cabin and the cockpit areas is what is used to ventilate and pressurize the compartments containing the avionics equipment and the cargo holds before being dumped through the two outflow valves back out into the atmosphere. So on the ground, the ECS unit is powered by three different options. First is a ground power cart, which is connected to the aircraft, and that will be able to power the whole aircraft ECS system or EC system. And then you can hook up an auxiliary power unit (APU), and that can power it as well. And the third option, if you're on the ground, is you can use one or both of the engines. You can use either the left or the right or both engines for this. And then during flight, obviously we're not going to have a ground power cart connected or an AP or be utilizing the APU for this. So we're going to be using the bleed air from the engines, and it specifically comes from the 10th stage bleed air, and that's what powers the ECS. On one of the first diagrams on the slides, you can see the CRJ-200 air conditioning and pressurization system, and you can see the whole thing. At the very bottom, you can see the ground power unit or the auxiliary power unit, and then on the left and the right, you can see the left and the right engine, and the red line coming from the 10th stage bleed air shutoff valves. And those are going to go to the two packs, which is the left pack and the right pack, before it gets into the distribution manifold to go all through the aircraft. So the air conditioning system, it's powered by the APU. It can be powered by the low pressure air or AC electric power. So when it is powered by the APU, the LCV valve must be open, and the 10th stage isolation valve is open. Left and right packs both on, and then you can adjust the temperature as required. If it's powered by low pressure air, then you just select the right pack on and left pack off for max airflow. And then the powered by AC electrical power when on the ground, or if unavailable, right engine is started by DC or battery power in order to establish the AC electrical power for the aircraft. So the left pack is primarily supplies the flight compartment, which it says 70%, and then it supplements the flow to passenger cabin 30%, whereas the right pack is opposite, primarily supplies the cabin 70% and supplements the flow to the flight compartment 30%. However, either pack is used simultaneously and can supply conditioned air to both compartments. The cooling efficiency of each AC pack is enhanced by ram air cooling via a heat exchanger. So rather than solely providing the power from the packs, you can use ram air. So ram air enters through an inlet at the base of the vertical stabilizer, so the rear of the plane, and it passes through the pack heat exchanger, and then it exits overboard. So the reason for this, one, it helps out the packs, but two, in the unlikely event that both packs fail, both left and right, then ram air can be used to cool the aircraft. So, both fail, then you're not stuck with no control over the temperature or pressurization. You have RAM error, or for the AC, RAM error. And then the flight compartment and the cabin, they have independent temperature control systems, so you can have the cabin one temperature while the cockpit's entirely different. Both the right and the left air conditioning packs should be used for maximum cooling. I mean, you know, one supplies 70% to the cabin, while the other supplies, it supplies 30% to the cockpit, and vice versa. So to get the full efficiency, you need to be using both. And in order to use just the left pack, you have the 10th stage isolation valve closed, and then for the right pack, you have the 10th stage isolation valve open. You can independently control the cockpit and cabin temperature, and one thing I thought that was really cool about it is that the climb capability of the aircraft is calculated based on the normal AC air conditioning operation on. And so it allows all engines to provide 500 foot per minute climb rate with the AC on, which is pretty cool. Single engine cruise performance is also calculated based on the normal AC operations, which is something you wouldn't really think would be the case. And then you can see the diagram here of the air conditioning unit, where it comes from. You can see how it flows. You have the RAM air inlet, and then it goes to the two packs, and throughout the aircraft. So some limitations for the air conditioning is that the bleed air extraction from the APU, the auxiliary power unit, for the air conditioning is not permitted above 15,000 feet. So the bleed air from the APU you cannot use over 15,000. The huffer may not be used to operate the air conditioning unit, as this may deplete the bottle, making it unusable for engine start. So this is something that you can hook up to the aircraft to start the engine, and you cannot be using it for air conditioning, otherwise you can't start the engine, potentially, if you deplete it. Another limitation, you may not use external high pressure air to power the air conditioning. It's not allowed. The manual cooling mode temperature, so these typically run on automatic. They do it themselves. They work by themselves, and so you can switch it over to manual cooling mode, but below 3 degrees Celsius they will start to develop ice, which is very problematic. And then if the packs from operation reach 85 degrees Celsius, then they'll shut down automatically due to the heat. So for the pressurization system, it controls the escape of conditioned air from occupied areas. It's the maximum differential has cabin altitude around 8,000 feet, while the actual aircraft is flying at 41,000 feet, flight level 410. So the cabin altitude rate of change is limited to 500 feet per minute while you're in a climb, and 300 feet per minute in a descent. So no matter how fast the aircraft is climbing or descending, the cabin pressure is not going to climb faster than 500 or descend faster than 300 feet per minute. And it's controlled automatically, as I said, by two pressurization controllers. There's a main and a standby controller. So the point is that if both fail, then you can still control it manually. If the cabin altitude ever reaches 14,000 feet, oxygen masks automatically deploy. It's 4 phases. There's a ground phase, which no pressurization valves are open because they're on the ground. Takeoff phase, thrust levers advance, pressure goes to 150 feet below the airport elevation. The whole point, so the pressure is below the airport. Climb and cruise, automatically adjusted by the cabin altitude. Aircraft altitude schedule program, 500 foot per minute for climb, 300 for descent. And then for landing, the cabin altitude decreases to below field elevation, then increases by 500 feet before keeping the valves open, so there's no pressurization. While landing with manual pressurization control, procedures must be completed, so it's the QRH procedure must be completed. Before landing, the flight attendant must be informed to wait for the signal for the flight deck crew before opening the passenger door. And So basically, the flight deck crew must ensure that the differential pressure is zero, meaning the aircraft pressure and the cabin pressure are zero. They're the same before you can give the flight attendant the okay to open the door. And then during a flight check for the aircraft, the flight deck must climb to 20,000 feet, flight level 200, and verify that the pressurization functions normally. So in the event of pressurization loss, oxygen masks must be donned and then establish communication. The pilots are going to turn to avoid terrain, and then they must descend no lower than the grid MORA for the current sector as published on the high-low altitude en route chart. We're contacting ATC, and then we're proceeding direct to the nearest low altitude airway. And when once we're established on that airway, you descend to the minimum en route altitude, or 10,000 feet, whichever's higher. So basically the point you're getting on an airway that you know what the highest or lowest altitude for train clearance is, and you're flying there, or 10,000 feet. And then you're going to proceed to the destination or to a suitable diversion airport. So some pressurization limitations. Basic passenger oxygen system is certified to provide a minimum of 12-minute supply. So you're at least going to have 12 minutes. The maximum relief differential pressure is 8.7 psi. The maximum negative is half a pound per square inch. During taxi takeoff and landing, the pressure differential must not exceed 0.1 psi. The aircraft must be completely depressurized prior to opening any of the aircraft doors, which makes complete sense. In manual mode, cabin pressurization must not be operated to minus 1,500 feet. And then when low pressure air source is used, the passenger door or avionics bay must stay open. So that pretty much concludes the environmental control system for both the air conditioning and the pressurization system for the CRJ200.